Okay, we're not gonna spend a lot of time today reviewing, but we'll have a test. We'll be in the testing center Thursday and do before class the following Thursday. So you got plenty of time to prepare for it. Of course, that gives you plenty of time to procrastinate on the things you gotta do in the meantime. But don't do that. Keep up with your assignments and do some kind of a disciplined gradual review, 30 minutes a day, whatever, okay? Now, it's sometimes impossible to do that, you know, when you're up here behind an alligator. Uh, you forget that your objective is to drain the swamp. And you get in that situation in any rigorous career. You try to discipline yourself so you don't, to the, as much as possible. You know, a little that's when it happened. Okay, vectors, we've got dot product, cross product, here's the projections, okay? But you can see all the expressions, progressions. I'm not gonna go over them with you. We've gone over it many times, okay? If you want to see a more thorough review, I can go back and find the video I did on this. But projections are real important. You're gonna have to do projections. You're gonna have to understand projections, okay? Now typically I can ask the question that, yeah, just do this projection. Okay, now tell me what the heck it means and tell me how it was constructed. So like 3 levels of the problem. One's just straightforward. You can do it. Okay, that's passing. Next level kind of separates the B's from the C's and D's. And the next level is designed to separate the A's from the non-A's. Hopefully everybody makes an A, but you know, you're gonna be challenged, okay? Okay, then playing through point X naught, Y naught, Z naught, perpendicular, some normal vector, and there's the criterion. You're on the plane if this dot product is 0. Line through X naught, Y naught, Z naught parallel to B. Well, it's just that vector from X naught, Y naught, Z naught to X has to be a multiple of V. And that leads you to this, also leads you to the symmetric equations, which I haven't written down, but you should understand. You just eliminate T from parameter space and you get 3 equations. Excuse me. A path in space is a vector function R of T. We usually use T, but sometimes we use S, which is usually interpreted as arc length. And there's a simplifying factor if you do this in terms of arc length, okay? Because then the derivative of R of S is always unit tangent vector. Is always a tangent vector, okay? It's always, yeah, okay. Anyhow, then your R prime, yeah, you just take the derivatives of X, Y, and Z and X prime I plus Y prime Z, J plus Z prime K. If T is interpreted as time, that's a velocity function. And you can think of it that way. Now, if you do it in terms of the arc length parameter, no, it's not the velocity function anymore, but it's got another interpretation you want to think about. Okay, unit tangent vector is this, okay? But of course, if you're doing it in terms of the arc length, if R is a function of, say, S, arc length, the magnitude of R prime is 1, which means you automatically get a unit vector. Okay. And T prime is normal. Okay. Now calculating T prime, I said, is good for the soul. Okay. You got to deal with the big expressions. You got to get used to it. You got to see a lot of big expressions. Deal with some of them. That's a good one to deal with. And then think about what it means. Just doing the derivative is good. Okay. Take a whole page for even a pretty simple R function. Maybe more than a page. And then you get your unit normal because you got to divide this by the magnitude of T prime, because T is a unit tangent vector. That doesn't mean its derivative is a unit vector. Okay. Unless maybe it's our arc length function. Unless your parameter rise in terms of the arc length. Okay, now going to the velocity, well, to the time parameter, okay? If R is parameterized in terms of time, then R double prime is acceleration. And I really should have a qualifier in there. I've never had to make a modification in this, but I'm always up for it, okay? if your parameter is time, then R double prime is your acceleration and, R prime is your velocity. And you project R double prime onto your unit tangent vector, you get the tangential component of R double prime, which is a component of your acceleration in the direction of motion. That's the one that pushes you back in your seat or makes you feel like you're being pushed back in your seat. Okay, actually, the seat's pushing on you. You're not pushing on it. It's pushing on you to achieve the acceleration. If you then subtract that projection from R double prime, it's going to be perpendicular. Okay, and we've drawn that out. I've emphasized that at least twice, maybe 3 times. But here's your picture. Okay, and then you get an osculating circle in the plane. That contains R prime and R double prime. Okay, it doesn't matter if this is time or not at this point. That plane, that defines your plane. So the normal of the plane would be the cross product of these 2 vectors. And I think maybe I say that, but maybe not, because that seems to be kind of automatic. So, I got some expressions here that come right out of what I just said. And then you have your binormal, take your unit tangent by your unit normal, call your binormal. Gives you a 3-dimensional coordinate system that goes along with your motion. The plane of motion is always perpendicular to your binormal. Here's your unit tangent, unit normal, binormal is perpendicular to both of those. Okay, so as your unit normal changes, you bank your turn or whatever, if you're flying a plane, you got those vectors. Okay, we got quadric surfaces. In general, it's this with x squared, y squared, and z squared terms, as well as x, y, and z terms. And that then we can complete the square and get this form. If h, k, and p, h, k, and p are all 0, then you have this form, which is the one we've pretty much looked at. But if you're not in this form, you can always complete the square and then change your coordinate system. You have an x prime, y prime, z prime coordinate system with x prime equal x minus h, y prime equal y minus k, and all that stuff. And you can do everything that we've done in that coordinate system. And then if you want, translate it back to the original coordinate system. Okay, that's pretty easy. I'm probably not going to have you do that, but it's good to know that you can do that. And it's kind of an important idea. There's a limit to how much I can really reasonably ask you to do, since we're going up all the way through the integral theorems. Okay. Then, I actually classify these. If A, C, and E are all positive, and G is greater than 0, you want G over here to be greater than 0, the right-hand side, then you're going to get an ellipsoid, because you divide both sides by G, you get the reciprocals of your major, semi-major, semi-minor axes, okay? So get your ellipsoid. Otherwise, if they're all greater than 0, as long as A, C, and E are non-zero, and I don't think I necessarily qualified that. Otherwise, A, B, and C are all non-zero, you have a hyperboloid. Now, if one of them is 0 and then you've got a y term up here, then you have a paraboloid. Now, you should be familiar with that because you did those assignments and did well on it. So a little bit of a misstatement there. And then the intersection with each coordinate plane, in the case of an ellipsoid or hyperboloid, it looked like this. Well, that's how we construct them. There's your semi-major axis, there's your semi-minor axis. Okay. If it's x squared minus y squared equals 1 or something like that, it opens this way because y can't be, x can't be 0, so you're not going to get points there. If it's like a y squared minus x squared equals 1 or equivalent, then x can't be, y can't be 0. Okay. Now you have this point or this point, otherwise not 0. Okay. And those are your intersections with the planes. You put all that together into contour lines and stuff. You get the picture of your quadric surface. You try to sketch your quadric surface. So you get you at least get your hands on the thing, so you get some kind of a general idea. And then we have arc length and curvature, which I don't think I addressed here. I might address it on the other side, but since I put them in parentheses and circled it, it means I kind of didn't cover right there. Okay. So you just ask yourself, what's the arc length due to interval of your parameter? And the answer is obvious, if you understand the connection. Okay. So you might go back to how I explained it, and you might ask me to explain it a little more, but not today, because today we're going to do this. Okay. Now what's this? You got some surface in XYZ space. Maybe it's a quadrant surface, maybe it's not. This one certainly isn't, because we do a plane where x equals constant. That's like the green lines here, and that intersects the surface wherever it is on some curve. Does that make sense? So we got some curve out here, y-axis goes that way, we cut it for some constant x, okay? And we get a curve, okay? The partial derivative of the function at the point xy, the partial derivative with respect to x, because it's x that's with y, since y is changing, is just the slope of this little vector here. It's the derivative of this function where we've restricted the function of two variables by holding x constant. Okay. And now we've just got a curve and it's got a slope at that point. There's your derivative, assuming all the limits and everything are defined, assuming you've got continuity and differentiability. Okay. And of course, we can then cut it for the constant y, and we get this blue surface that I'll probably draw a little better here in a minute. And that thing has a derivative with respect to x. Okay. And it's really easy to understand how to calculate it. Understand how to use it. Well, okay. So what I say here is the partial derivative. We're using that little curly partial derivative sign, that nice smooth thing. It's easier to write than a D. So it's always joy to encounter it. Okay. The partial derivative of f with respect to x is just the derivative of f with respect to x within the plane where y is a constant. That makes sense? Well, here's a plane where y equals constant, and there's a perfectly good curve, assuming you have a smooth function and all that stuff. Okay. And we'll talk about the details of what we mean by smooth and continuity and all that stuff. I mean, you've encountered that in the second section of the chapter, okay, which is due today, and I think everybody's doing okay with, I hope. Again, I've been looking at too many things, and there are too many bizarre things that are happening. So it's a little bit of a blur. But last thing I looked at was pretty good. So, okay, so the partial depth with respect to x, again, at the point xy is just the slope of that curve that we get when we slice the surface. Okay. Sorry, I'm telling you the y is constant in this green thing. Y is constant on the blue curve, right? So this slope. It's a slope of the blue curve at the point x, y, f of xy. What are the coordinates of this point here? Well, you got xy down here, and above it, how far do you go? Well, f of xy. That's how you graph a function of two variables, right? Plug in x and y and tells you how high to go. Tells you what z is. Okay. And that should be familiar. You've done that. Now, there's more to it, and just anticipating just a little bit. This vector here, I say, is I plus a partial depth with respect to x times k. Okay, so what we're doing is we're coming one unit in this direction And what's our rise? Our rise is the change in X times the rate of change times the derivative, okay? Just using the whole idea of a differential, but I probably ought to draw some pictures about that to refresh you, because nobody ever really remembers a differential or really learned to use it first year calculus. Well, I say nobody, very seldom does anybody, some people do. If you did, great. But I assume I'm gonna have to refresh on that a little bit. Okay? And then J plus the rate at which F changes with respect to Y times K gives you a rise over run equal to this partial derivative in that direction. And now we've got two vectors here that are in the plane tangent to this surface at this point. We take their cross product and we get a normal vector. And now we know the coordinates of the point, we know the normal vector, we know the tangent plane. And we can use the tangent plane to do a differential approximation of our function of two variables in the neighborhood of this point. Ain't that neat? Well, we're gonna do a little slower because that's what we're doing today. Okay. We're just putting this into the context of everything else. And then we get directional derivatives. And, you know, we get that. I think that might be next time. Okay. Have a look at the schedule and see how much I need to cover. But we'll probably talk about it somewhat today. All right. Yeah, we got a question. Hang on. Okay, now this is kind of most of the rest of the course. I mentioned for line integral, we parameterize our curve. Well, we do that for an arc length and stuff. We do it for more general things. And we'll see how that works later. Okay, because it gets a little bit involved, but it's not terrible. So all the stuff from here over to here, well, I'm kind of moving. I'm not really moving from earlier to later there, because we do coordinate systems, we've already done them, and that's the reason I'm putting this board up, okay? We have to know how to convert coordinate systems. We get over here to conservative fields, and right here, I don't see the integral theorems here. Well, this builds right up to the final thing, which is the integral theorems, okay? Now we're gonna have moment integrals and stuff like that, but we're gonna do three-dimensional integration. That's chapter 15, and we're just moving into chapter 14. Yeah, kind of getting into the middle of that chapter. The other thing you need to know for the test is your coordinate systems and your volume increments in the coordinate systems. Okay, which we talked about last week sometime, I think. And we drew the pictures. Okay. If I'm going to be nice to you, I'll stick with a cylindrical coordinate system. But if I feel like I'm not doing enough challenge, I'll throw in spherical. Cylindrical is a little easier to draw. If I ask you to draw something, it'll probably be polar in 2 dimensions or cylindrical in 3 dimensions. Okay, should be able to draw the increment shape. Explain why it is. Right there is what you do the polar coordinates. And I drew it all out, so you might want to review it and review the text. Okay, review those pictures. You ought to be able to draw those pictures. I remember drawing those pictures when I took this course at least dozens of times. Okay, every time I ran into something, I draw the pictures, make sure I understood what was going on, and reinforced it. So when I got to the test, I nailed it. Okay. So hopefully you'll all do the same thing. But whatever learning style works for you is great. Doesn't have to be the same style I use. Okay, so let's work out a few details. I've got enough force space here. Indulge myself in a full piece of chocolate here. So be prepared. Oh, that's recording while I did. Okay, sorry. Okay, partial derivative. You saw the picture. Let's draw it slowly. Here's set of rectangular coordinate axes. And here's a point. We'll call x, y. And there's some function. Z equals f of x, y. Tells you for any x, y, what your z coordinate is. So you got x, y here, and you got a z coordinate up here. So that the length of this, or a vector, a directed distance, the displacement from here to here is your value of f of x, y. Okay, so that's familiar. So the z coordinate here is your f of x, y. Okay, so okay, I'll stick with the same colors I used. If I don't see any blue chalk, we don't have a lot of blue chalk. Well, it's that. Blue chalk. Okay. So we got everything we need. Okay. Now on the picture I just showed you, I have x is temporarily constant. And we've got a plane that lies above this line. Then we know that this plane intersects the graph of f of x, y. Assuming f of x, y is defined for all the x, y's above or and or below this point, right? Or up above and or below this line in the xy plane. So this is a plane, x equals constant. It intersects our graph on some curve. So that's what this curve is. For x equal whatever this constant is, you've got this function. Then the tangent line at this point this line restricted to this plane is your tangent line. Okay. So if we sketch, I'll just do this. If we sketch this curve again, slope of the tangent line is, well, it's the limiting value as delta x approaches 0 of the change in the value of f, which is f of x y plus delta y minus f of x y. So we've got y here. And this axis goes in the y direction. And let's say we got a y plus delta y. And of course, this distance here is delta y. So we have this point and this point and a secant line from here to here. Okay. Now the secant line differs from the tangent line, but the closer delta y gets to 0, the less and less it differs. So it's like we've got a secant line from here to here, then a secant line from here to here. And the slopes of these secant lines keep getting closer to the slope of the tangent line. Does that make sense? Okay, the shorter the part segment of the curve you calculate the slope on, the closer it gets to the slope of the tangent line. That should be something that's very familiar from first year calculus. You might need to review that if it isn't. Okay, now it's this, which is your change in F over the delta y. So it's like here, you have delta F here to here. And delta y here. So the slope of this is delta F over delta y. Okay. You have a similar triangle here that I'm not going to label, but it has a delta F, which is this vertical side, and a delta y. And the ratio of delta y to delta F is different here because this thing has some curvature. And the whole thing approaches the derivative. Okay, so the tangent line is this. The limit, and I have delta x going to 0. Sorry if that's misleading. Should be delta y going to 0. This is a partial derivative with respect to y evaluated at the point x, y. X is the same here as it is here because you're in the plane where x is constant. So that's what this expression means. Now, for a given function, you're going to have to evaluate that. There are at least a couple of problems in the problem set that ask you to work out the algebra. Okay. Then we might work one out. If we have time, we will. But once you get the concept, that's what's going on. And that's all that's going on. So you want to explain, you want to understand that. Because you want to understand what a derivative is and what it means, because if you start using them when you're analyzing the stresses in its structure, or when you're analyzing the dynamics of a particle, or the dynamics of something you're modeling in hyperdimensional space, you have to understand this difference quotient. Something you see first in pre-calculus, then you perfect it from one dimension in calculus, then you perfect it from multiple dimensions in third semester calculus. Okay, multivariable calculus. So get that. Okay, then of course we can do the same thing Well, if I can get the right line through X, Y. Okay, so now we have Y equals constant. That plane extends forever, but I'm only drawing it up to here because that's as far as I need to go. And I'll do something similar with the plane Y equals constant. I'll come up to, let's say, try to come up high enough. Come up about here, move off parallel to the X axis. I'm going to this point, and then it could be clear now what this blue plane is depicting, and there's going to be some other curve. You don't know how the function changes as you move this way or this way. Okay, so maybe it's I've lost my point here. And let me label this point. This point is X, Y, obviously, because the X and Y coordinates are this. And then Z, which equals f of X, Y. So that's X, Y, Z, but Z is on the surface of this graph. Okay, Z pushed to the surface of the graph. So there's the point. Okay, so now you got some curve here. Okay, well, in this plane, maybe the curve does this sort of thing. And now you have a tangent line within this plane. Okay, so in the plane, Y equals constant. And I'm not going to do the similar sketch. You can just sketch similar to this. Slope of the tangent line in the plane Y equals constant is the limit. Well, now X is changing. Delta X is going to approach 0. It's going to be f of X plus delta X Y minus f of X Y over delta X. And that's the partial derivative of f with respect to X at the point X, Y. So you can visualize it. Now I added a couple of things. I added a vector along the tangent line in this direction and a vector along the tangent line in this direction. And that gives me a normal I'm going to draw it since we got this context. Okay. I'm going to draw this curve in the XY plane. As X increases, my curve, and it starts up here, comes down and does this and comes way down. And here's my point on the curve. So here's my X coordinate to that point XY that I have there. I should probably put subscripts on it, but I want you to think of the point as being variable, so I don't want to do that. It's a, there are advantages both ways, some disadvantages. Okay, so we have this. We have this tangent line. And the slope is partial f with respect to x and fy. And of course, the line segment here is z equals f of xy. Keeping in mind that y is constant, because we're in this plane perpendicular to the y-axis where y is constant. Okay. Any vector from this point down here has a rise and a run. So it has a slope, and the slope is equal to the partial derivative. So we want the vector here for which, I'll use a different color. What could I use? Yellow. Not yellow, but yellow. Okay. Oh man, the chalk is screwed up. Hopefully this thing. Okay. You know what I'm going to use for this vector? I'm going to make this the vector I. Okay. Then what's this vector? First of all, what unit vector is it a multiple of? Hang on. Okay, so my question is, if we choose this to be the I vector, which is convenient, you'll see why in a minute. We choose the I vector, and then we come down to the tangent line with another vector. Well, this vector is a multiple of k because it's in the z direction. Okay. So it's some multiple of k. And we want to fill in the number there, or the quantity. So what multiple of k is going to be? Remember that the slope of this tangent line is this. We've got I here. We have the partial of f with respect. We have the partial of f with respect to x evaluated at xy. Okay, I love this so much. I just get choked up over it. Okay. So if the slope is going to be this, then how long does this vector have to be? How long is this vector? It's 1, and we got a conjecture here that that's going to be right. Slope is rise over run, right? Here's your rise, here's your run. If you divide the rise by the run, you're going to get the slope, which is this. Okay. So this has to be the slope times your k vector. Okay. Because how long is this vector? Well, it's equal. It's got a length that's equal to the slope because the k vector is a unit vector, right? Now, when I say the length is equal to the slope, actually, the slope is either positive or negative. In this case, it would be negative, right? I mean, if it's as I've drawn it. So you have some negative multiple of K. So the rise is whatever the slope is. Since magnitude of K is 1, right? So yeah, this vector is slope times K, the rise is a slope. And the run equals 1. Size of unit vector, right? So you can write out as an equation, I mean, rise over run equals slope. If we do rise over run, we get slope over 1, right? This confirms that the rise is a slope, and that's what it'll be if this vector is slope times K. But of course, the slope is a partial derivative with respect to X. Okay? Pressing the X, Y, it's understood that we're evaluating this at this X coordinate and we're the plane where Y is whatever it is. Okay, now we made a good observation. Somebody said, yeah, I mean, I'd said it before, but I said it fast and it might not make the impression, so it might seem new, but yeah, you're going to get two vectors here. We're getting one of them right here. We haven't drawn it yet, but it's going to be along the tangent line, okay? And we're going to write out its coordinates. We can do the same thing over here. So now we've got two vectors. They're both tangent to the surface. And as I said quickly before, if we take their cross product, we get the normal. Once we have the normal, we have a point here, so we get the tangent plane. And the tangent plane approximates the surface in the near vicinity of this point, assuming that the surface is multiply differentiable in both directions, so that it's nice and smooth, no jumps, continuous, and so forth. Okay, well, let's finish it. Okay, so what we're really trying to do is we want to get this vector here. Well, I didn't put a head on it here, but there it was. So this vector well, it's I plus partial of that with respect to X times the K vector. I mean, it is because it's this vector plus this vector, head to tail. It's I plus partial with respect to X, partial of F with respect to X at K. Now, if we do the analogous thing in the X equals constant plane, then the tangent plane is in the direction of J plus the partial with respect to Y times K. Okay. Now, I'm gonna have to go back and sneeze a little bit. It's me every once in a while. Okay. I don't know what kind of particles came in through the door when y'all came, but Actually, it's been happening all morning. Um, still know if it's a cold or allergies. Go back and forth on it. But in case it's a cold, I'm gonna do my sneezing away from you guys. At least with my arm. Okay, so anyhow, thus. So, well, what's the cross product? Go ahead and write out the cross product. Try to clear out the sneezes that are trying to take over my body here. Should take us a minute, usually only lasts a couple of minutes, if that. Okay, well, ask everybody to calculate this. You don't need determinants. You only have three things to do cross products of. Okay, first of all, distributive law applies. I cross J is K. Okay. Then I cross K is, here's I, here's K, there's negative J, right? So you're gonna have negative partial F with respect to X times K. And what's K cross J? Well, it's negative I. K cross J. Here's K, there's J, and there's your thumb. Pointing in the negative X direction, which gives you negative K. If you haven't done enough of that to make that really quick and natural, you need to keep doing it. Okay? Don't just put the things in the determinant and calculate them. Yeah, if you got three components to every vector, do, but if you only got a couple of components in each, or just review, what's I cross K, what's a K cross I, and all that stuff. Because it can be very helpful in visualizing stuff that's relevant to almost anything. More room, and I knew that when I did it, but there it is. So M this is wrong. I don't know what I've done. Oh, that's I. So first of all, that's I and this is J. I mean, I said what it was, and I wrote down K. Okay. So we write that as negative partial F with respect to Y times I minus partial F with respect to X times J plus K. Then you ought to visualize that in various situations and understand how that makes sense. Okay. In any case, in this particular instance, the partial of F with respect to X is negative, so we're going to have a positive multiple of J. The partial of F with respect to Y is also drawn so that it's negative. Look over here. So we have a positive multiple of I. Well, how's this thing sloping? It's sloping downward to the right and it's sloping downward as we come along the x-axis, right? So sloping downward along the y direction and downward along the x direction. Tangent plane is going to be like this, going downward in both directions. Okay. So that the I component is going to be, the normal vector is going to be tilted that way in the positive J direction. And also that way in the positive X direction with a positive K on it. The K is always going to be just plain old K. These things determine it. So you want to think about that, but it's gonna maybe then look like this. I've got it in the screen. Okay, this is a normal vector. If you want a unit normal vector, it's just fine. Just divide whatever you get when you do this by its magnitude. Unless the plane is flat at that point, both of these, or at least one of these, will be non-zero. And the magnitude of K alone is 1. So this will always have a magnitude bigger than 1. Okay, so the unit normal, you'd have to divide by the square root of 1 plus the square of this partial derivative plus the square of this partial derivative. And that should be getting familiar to you, that whole idea, the Pythagorean theorem expressions. Okay. Well, that's more than I really needed to go over today, but it comes out of this picture so naturally. So we kind of anticipated stuff that's coming up in the next section, but both sections are going to be due next week. This week, whatever. Okay. I didn't make myself a note when they sent me. I think there are only 2 assignments due this week. So I think it's 14.3 and 14.4. Pretty sure of that. Because they're such important sections, they're kind of pivotal, and then they get into some really pivotal stuff. It gets more pivotal as it goes, but you got to understand this. Okay. Okay, well. Calculate partial derivative, very simple. And it should make good sense if you've understood what I've done, even to a moderate extent. And it does take some processing. You ought to be able to draw these pictures on your own and so forth. Okay. I remember it took some processing for me, even though my professor, Dr. Clark, good guy. We draw these pictures on the board pretty much beginning of every class for a week or 2. Okay. And refer to them. And I think that's pretty standard in teaching multivariable calculus. He did pretty standard stuff, but delivered it very nicely. Okay. Good guy. Okay, to calculate the partial derivative, let's just take a simple function. Two x squared minus 3 should have been xy. I wrote it yx, and that's kind of non-standard. So change my y to an x, my x to a y, even if it looks bad. Okay. So well, when you do the partial derivative with respect to x, you're holding y constant, right? So you just use your rules for derivative, but treat y as just a constant. If you treat y as a constant, then the derivative of 2x squared, well, that's 4x no matter what. Okay. The derivative of 3xy, well, y is constant. That's just 3y. And then derivative of y cubed, well, if y is constant, the derivative of y cubed is 0. Okay. So again, you just treat y like some letter that isn't changing. It's not a letter that changes with x. But tell me what you think the particle of f with respect to y would be. See if you can write it down. Just see if you get the gist of it. If you are getting the gist, I don't have to talk much about it. If you aren't, then I'll talk a little more. So if you want to shut me up, get it right or two. Okay, so now let's reduce partial depth with respect to y. Well, 2x squared, x is treated as a constant because that's what you have if you confine this thing to a plane where x is constant. And that's the picture we use to develop the whole thing, and that's also the limit derivative definition. So we have just plain old 3x minus 3y squared. Somebody read that as a square instead of a cube. Well, from back there, I couldn't see it either. But I remember what it was. Okay. And of course, the derivative of anything that doesn't have a y in it is 0. Now, naturally, we could do a function of any number of variables. F of x, y, z, w, u, v. Okay. Just write down the definition of the derivative. You hold everything constant, but the one you're taking derivative of. Now that's 6 variables. Probably don't want to try to visualize that. Okay. But if you confine it to one where everything else is constant, you just get a one-dimensional function, even if you got 6 variables or 1,000,000 variables or whatever. You get a one-dimensional function when you hold everything constant but that one variable. Okay. So you can calculate in any number of dimensions the rate of change with respect to that one variable. And it's no different than what you do here, it's just longer. Depending how long your expression is. Okay. There's chain rules, we'll get those next week sometime. Okay. And we want to understand the chain rule in a way that, you know, we want to deepen your understanding of the chain rule. You really want to have an intuitive grasp of what the chain rule is telling you. And now you look pretty good. So I wouldn't be surprised if most of you have a good intuitive grasp, but on the other hand, you're in a class where not everybody was at an equal level, although everybody appeared to do pretty well in that class. Okay. But y'all are pretty good. Hopefully your instructor was able to convey some of that. Now, again, when you're in a class where not everybody's going to understand it, you got to do limited amount of that. Not sure how that balanced out. And I'm not trying to evaluate his class, just trying to comment on the fact that maybe you've got a decent grasp of the chain rule and maybe you don't. Probably you can use it. Do you really understand what it's telling you and why the derivative of f of g of x is g prime of x times f of g of x times f prime of g of x, okay? What's that? It's because x is driving a change in g, okay? And then the change in g is driving the change in f. It's that simple. It's very simple when you understand it. And it makes things a lot easier when you look at the impossibly complicated expressions you get when you start doing the chain rule in its various forms in multidimensional spaces. Okay. Keep your wits about you and understand what it's telling you. You can always remember what the chain rule says. All right. And we'll talk about that. You know, that's coming up, not this week. I'm not sure what else. Okay, so let's try another one. What in the world can I mean by this? It's a second partial because you're going to take a partial with respect to x and with respect to y. You're not going to multiply these partials. What you're going to, I'm going to tell you, I'm not going to drag it out of you, much as I love to do that. By this, we mean take the partial of f with respect to y, and then take the partial of that with respect to x. So you should be able to do that. Got a question? Whoops. No, we don't want to stop recording. Okay, some people got it. Okay, I'm not even gonna bother to look because it's really easy. And if you didn't get it, you will. What's this mean? This means partial with respect to x of partial with respect to y is 3x minus 3y squared. Holding y constant because you're doing the partial with respect to x, this is going to give you 0 and that's going to give you 3. That's it. Okay. Then if we do it in the opposite order, we do the partial with respect to x first, then the partial with respect to y. We get the partial with respect to y of what we got for the partial with respect to x, that's 4x plus 3y, which again equals 3. Now I'm just going to say it in general, you take the derivative, limit derivative here and the limit derivative for x, and you combine them and just parse your expression. And I think your text will do that. So you probably want to take a look at it and see how that's parsed. But it just parses out and everything works out so that it has to be the same both ways. And it's not a difficult proof. Okay, still significant. So it's kind of handy. Now we can get into the geometry of it, but I'd want to draw more and I wave my hands that much. You know, my hands are probably going to get twisted up and confused. Okay. So we might look at the geometry of why that has to be true. Okay, you probably ought to, you can bring yourself to think about it some. Okay, I'll just comment that once you get the equation of the plane here, it's going to be for any x, y in the vicinity of this point, the y coordinate on the plane is going to be pretty close to the y coordinate of the surface. Because it takes a surface a while to curve away from the plane. Now, the faster the surface curves away from the plane, the quicker that approximation deteriorates. But that's just like differential. So let me just review. I'm not even going to review, I'm just going to write it out. Okay, here we have y, x, and some function. Y equals f of x. And we'll take some point here. And here's your tangent line. And here is x. And here's x plus delta x. Because the curve is smooth, x plus delta x stays close to f of x. I'm sorry. F of x plus delta x stays close to this equation of the tangent line. What's the equation of the tangent line? It's okay, I've got to use an x naught here. And that's what, so x equals x naught plus delta x. Now that's a straightforward y minus y1 equals m times x minus x1. It just says that this partial derivative is the change in your y coordinate, which is y minus f of x naught. Compared to here, minus over x minus x naught, which is your change in x, which is the slope. Okay, so slope is approximately equal to slope. So in differential form, you write df, the change in the value of the function is the rate of change of the value of function by how much x changes. Rate of changes is the change in f with respect to x at your original point, and that's the slope, and the slope isn't changing much if you stay close. Okay. And that'll be the case whenever your derivative is continuous. And continuously differentiable, I think.